This is my plan for today's lecture. First, I will start for students and everybody with a little introduction to what are the key observations we have at the moment to answer these questions or to approach this question. And then I will come to the theoretical part, which is concerning the equation of state. In our case now, hybrid equations of state with a nuclear or neutron star part with a nucleonic matter and a quark matter part. And the question how to construct a phase transition. So here I will dwell on recent ideas to construct not just Basta or Maxwell construction, but use interpolation, which may have even some physical interpretations. Then I will discuss the hybrid star solutions. We will test with Bayesian analysis against the priors from the multi-messenger data, which of the models have the highest probability of being true. And we can also, with this Bayesian analysis, we can we can explore what would happen if an experiment, an observation would be more precise, if the result would be a little bit different from what it actually is. And so I will report on such investigations. And finally, I would like to come to the finite temperature generalizations, which brings us then close also to the discussion of the QCD phase diagram, which is another community, mainly to explore it in heavy ion collisions. And here in the heavy ion collision community, the phase diagram height, which is called little bang, and the low temperature end with the high densities, where in particular Neutron will be operating, but RIG fixed target is producing data soon. And at CERN, we have the SPS and the LHC, particular SPS. Yeah, and in addition, we call this the femtonova in heavy ion collisions. Okay, and I will report here our investigations based on finite temperature hybrid equations of state, first order phase transition. What could be striking signals of a phase transition in supernova simulations and in merger simulations? Okay, so to start with, in introducing the topic, I refer here to the recent Nature article by Emily Anala and the Finnish group. And what they do, they come perturbative QCD region. Here on the left-hand side in the pressure versus energy density region in the equation of state of perturbative QCD, where we seem to know what is going on the basis of analytic calculations in QCD, but unfortunately this is at extremely high energy densities which are not present in compact stars. And on the other hand, we have a well-explored nuclear fixed territory, and now the compact stars in between, they might help to interpolate between both. And this is actually where the colored region is, and what the group in Finland conjectured is based on the following idea, basically, that quark matter, at least the perturbative quark matter, should be close to the conformal limit for massless particles, which has a speed of sound squared of 1/3. Nuclear matter and interacting matter generally can be different from that. The speed of sound squared should be less than speed of light squared, so the causality constraint shall be fulfilled, but the speed of sound can well exceed also. Now what they do is they extrapolate or interpolate from the perturbative QCD to the region where we can extrapolate from nuclear, and one can then define matching points. And one of such matching point could be, for instance, at about twice nuclear matter density. And then one would predict with such an interpolation hybrid star with a large quark matter core. So at 2 solar masses, the star would have then a 12-kilometer radius, and more than half of the radius is quark matter. Okay, there's a caveat to this very nice work. The caveat is that quark matter can well have also a speed of sound which exceeds 1/3. And for instance, in color superconducting CFL phase, we know that. And there, of course, it depends on the strength of the coupling, which is non-perturbative and is not well known. It's a model quantity. And on the other hand, if we would not base our constructed equation of state on some on some piecewise polytropic or on some interpolated equations of state, we will discuss, for instance, a first order phase transition, then the pressure would be constant in a certain region of densities or energy densities, and this would entail the speed of sound squared is 0. Then, of course, one has effectively softening equation of state, and this has an influence, of course, on the structure of the compact stars. So we will, in this talk, we will discuss this region where a phase transition could happen. So we will favor the region of pressures below 100 MeV per meter cube. And I will try to convince you that the phase transition actually can happen in this domain, and that here we could already expect quark matter effects. Whereas in the Nature article, you find the conclusion that more or less a transition is where the slope in this double logarithmic plot pressure versus energy density changes. So just at the upper limit, what we would consider as realistic for a quark-hadron phase transition. But that will be the part of the main contents of my talk. Yeah, we start with general relativity, and we had the international workshop on astronomy and relativistic astrophysics. So compact stars have always been one of the key playground for also alternative theories of gravity, but here I will be solely based on general standard general relativity and the Tolman-Oppenheimer equations, which are given here with colored pieces, which show the general relativistic corrections beyond the Newtonian case. And here we see the role which the equation of state, P versus epsilon, plays in this business, and also what the modification of space-time in the vicinity or also the interior of compact stars will play a role when we insert standard values for mass and radius of a massive pulsar, like 2 solar masses and a radius of, let's say, 12 kilometers, what we just have heard in this Nature example, the article example, then this is a factor 2 correction, this green part from the matrix. So we have to keep this in mind and always apply a Tolman-Oppenheimer so general relativity. Now, I would like to elucidate for you the one-to-one relationship between the equation of state and the mass radius curves, which is the basis for these ongoing investigations of observations of masses and radii of compact stars in order to finally infer the cold matter equation of state from these observations at densities which are not accessible at those low temperatures in terrestrial experiments. So starting with Tolman, Oppenheimer, Volkoff, who applied their equation for free neutrons, the blue line in the equation of state, just a free neutron gas, they got a solution for the mass radius relationship with a maximum mass of 0.7 solar masses. Of course, at that time, there were no observations of neutron stars, but nevertheless, if a neutron star should emerge in a supernova collapse, then it was conceivable that the mass should be higher. But before the year 1967 and following, we had no measurements of neutron stars as pulsars, and we could not infer the mass. Now we know that masses can be as high as 2 solar masses, and then clearly the non-interacting neutron gas is excluded. So one of the interacting nuclear matter models is a nonlinear Blaschke model, which is fitted to reproduce nuclear separation properties, and then you can extrapolate with this relativistic mean field model to higher densities. You put this equation of state into the Tolmod-Oppenheimer-Volkoff equation, and you get a maximum mass of around 2 solar masses, and the radii are in the expected domain of 12 to 13 kilometers at the typical mass of binary radio pulsars, which is around 1.4 solar masses. Of course, exotic matter has been always around as a hypothesis for the interior of a compact star. Here I give the example of strange quark matter within the back model. So this is just massless quarks. So you see a straight line of pressure versus energy density and a downshift by a back constant. So this is a strange quark matter equation of state, and you put this into the Tolmod-Volkoff equation. You get this typical curve, which for a so-called self-bound matter, which is bound by confinement, by the back pressure, and doesn't need gravity to be bound. So strange quark matter can be as tiny nuggets as possible. Okay. Now let's also discuss the central energy densities, which are of course very much interesting. So what is the critical density or energy density for the neutron star? And then we see that the stiffer the nuclear matter, so the higher the maximum mass as a characteristic parameter, the lower is the central density. So the highest central density we have for the very soft free neutron gas, and for stiff matter, the central densities are lower. So it is not true what one naively would expect, that the more mass you have in a pulsar, the higher the central density should be. No, this is not necessarily true. What about the experimental situation? So inferring the equation of state from mass radius measurements. So early work in also using Bayesian analysis has been done by Andrew Steiner, Jim Latimer, and Ed Brown 10 years ago. And they used the radius expansion bursts of compact stars in low mass X-ray binaries. And so these bursts, one could infer the photospheric radius. And once you have a radius and mass constraint, of course, you can invert the Tolmod-Volkoff equation and get a quite precise pressure versus energy curve here. Unfortunately, there are uncertainties with this X-ray burst inference of we have to do with the composition of the atmosphere of these objects. And unless we can determine the atmosphere composition, there are uncertainties which can amount to 2 kilometers, for instance, when you compare hydrogen and helium atmospheres. Therefore, one is looking for other possibilities. So let us come back to this in a moment. Now I shortly would like to rehearse with you the situation with the maximum mass. So we were all very happy when in the year 2010, 10 years ago now, the Demarest et al. Published their analysis of the neutron star white dwarf system, for which they could measure the Shapiro delay. And once you measure Shapiro delay, then this is a relativistic disentangle mass of both the pulsar and its companion. And here the red points are the measurements. They depend on the phase of our observation of the neutron star relative to the orbiting white dwarf. And we see this spiky behavior of the timing residual in this Shapiro delay allows to infer actually the inclination. Inclination here is very close to 90 degrees. So we are lucky that nature provides us with such an object where we can look edge on to this binary system. Now we know we have another system of this kind, which was published last year by Cromartie and others. And this turned out even to have a higher mass, the neutron star, in this range of 114 plus minus about 0.1 solar masses. So this is our record holder here, this pulsar in the mass radius plot. So actually here is the website. This is quite useful. It's of the Max Planck Institute in Bonn. And anytime there's a new measurement, they add it to this interesting plot. The lines which you see concern the different equations of state. And you see there's a broad variety, even if we can exclude those equations of state which cannot describe the maximum, with their maximum mass, the actually observed mass of this high mass 2 solar mass pulsar. But still there are enough equations of state which are stiff enough to describe 2 solar masses, but their radius varies broadly. So now the new situation is that we have the binary neutron star merger, GW 170817. And from the analysis of the gravitational waves, we can infer the tidal deformabilities. And this tidal deformability put now stringent constraint on the compactness of the star. And here we have the probability lines of the analysis of the LIGO team, actually a LIGO-Virgo collaboration. And this points to rather lowish tidal deformability, dimensionless tidal deformabilities of around 500. Only the very softest equations of state, like APR or Ring have tidal deformabilities in the range when we think of purely nuclear equations of state. Another point is when we consider the rotation, there has been constraint derived for the possible upper limit on the maximum mass of the compact star by Rezzolla and others, namely arguing that the differentially rotating hypermassive odd star will very quickly cool and become a stationary rotating, fastly rotating compact star at the Kepler limit. And at this, from the fact that there was kilonova observed after the binary neutron star merger, it could not have been collapsed immediately to the black hole. So there should this trajectory of the early evolution of the binary should at least cross below, just below the maximum mass of the rigidly rotating at the Kepler frequency hypermassive star. supermassive star, neutron star, which forms after the merger. So from this, one can derive the constraint, the upper limit, an upper limit on the maximum mass, which, if one would dwell on this, is a very important constraint. Now let us put these constraints together. We have discussed the maximum mass here, the blue bar in the mass radius plot. Now we have excluded regions, namely these bars at 1.4 and 1.6 solar masses from the phenomenology of the merger GW17 and we have just discussed the upper limit on the maximum mass. Now, we were waiting long time for first results from NICE. Finally, they came out in December last year. And these are mass measurements. And here is one of the error ellipse for this correlated mass radius measurements from the Miller publication. There's an alternative publication with a slightly shifted mass radius ellipse, which I didn't show here. Here we have the mass radius constraint from the tidal deformabilities of GW17, and these two constraints together with the maximum mass of the Cromarty pulsar we will use for our Bayesian analysis of hybrid star equations of state. Now, let us illustrate this situation where we forget about exotic matter in the star. So what if in a neutron star is just normal nuclear matter made up of neutrons and protons and electrons, the usual NPE phase of matter. For this, we have two types of descriptions. We have a description which is based on density functionals, so relativistic description of nuclear matter. Here I refer to the DD2 class of equations of state by Tidal and others. So this is the most recent parametrization, which is broadly in use. One can modify this parametrization at high densities. The index F indicates that this is a little bit a softening, this light dashed black line, softening in order to fulfill Danilevich's flow constraint from heavy ion collision flow measurements. On the other hand, one can also stiffen the matter by adopting an excluded volume of the nucleons. Then we arrive at the dash dotted curve here. So on the other hand, based on potential models, non-relativistic potential models and statistical physics of many-body systems, the Akmal-Pandre-Ravenhall equation of state has been derived, and this is one of the standard equations of state in use in astrophysics. That is the green line. And this green line nicely crosses all the constraints and does not cross into the fields which are excluded. So is everything okay with APR? Here I would like today to acquaint you with recent work by the Japanese group on the Yamamoto, Togashi, and collaborators, including also Thomas Reichen from Nijmegen. And they have analyzed, and now comes here an inset, they have analyzed oxygen-oxygen scattering at energy per nucleon of 70 MeV. Here, the black dots show the data of the angular distribution of the differential cross-section of this scattering. And when you insert into such calculations with folding potentials, the AV potential, which is the basis of the APR equation of state, then at large angles, you are off. Similar for the extended soft core potential of the Nijmegen group, you cannot describe the data. So this is the necessity to add some short-range repulsive potential, multi-body potential, which appears only when you collide nuclei or when you discuss nuclear matter. And as a theoretical model for this, the authors have used the multi-Pomeran exchange potential and have parameterized it in order to describe these data. So let us focus on the argon V18 based potential model here, the blue lines. And on the right-hand side, here you see the corresponding equation of state. So this correction by the short-range repulsive multi-Pomeran exchange potential not only helps in describing this oxygen-oxygen scattering data, it also gives us a much better correspondence with the nuclear saturation, which was always a problem in the APR equation of state on the AV18 potential. Now, when we take such a generalized potential with the short-range repulsion and put it into the Tolmot-Volkoff equation, we get a mass radius curve, which you see here in the lower right plot. And actually the best description would be this line where actually we are close to 13-kilometer radius, but let's be conservative and take a little bit softer correction here, this MPB potential, which has still predicts a radii of compact stars in excess of 12 variance with the APR equation of state, where we have seen that in most of the mass range of compact stars, the radius is around 11 kilometers. So now here, most of these results have been shown by the black and the red lines. And so the conclusion is that if we should abandon the naked, so to say, APR equation of state, is short-range multi-Pomeran function, then we spoil our nice correspondence which we had with the APR equation of state with the low values for the tidal deformabilities. And this is the ansatz here. Quark matter can help. So if there's a necessity to have a stiff nuclear matter at supersaturation densities, which are probed in heavy ion collisions, but also in compact stars, then this would help to have an early onset of a quark matter. And for this, I will discuss two things. So one is that we take as a basis the E2P40 equation of state, which is a rather stiff one, and discuss a phase transition to quark matter, where the quark matter model I will discuss in a moment. And what happens then is that we have hybrid star matter, so the mass radius curve then practically mimics the mass radius curve which we would obtain with APR. But as we have discussed just a minute ago, we should abandon APR because it's not a realistic interaction for nuclear matter, because in APR, the short-range repulsion effects are missing. So then, well, very good correspondence with the tidal deformabilities in the case of our hybrid star matter. And the only question is, so what is then the most realistic onset mass for hybrid star and the corresponding density? This we will discuss in a moment. The other possibility is that we say, well, APR might be not so bad for not too high densities. But when we reach nuclear matter density or beyond, then short-range corrections in the interaction may be due to partonic substructure, particular quark substructure, should become important, which stiffen the nuclear matter. And then starting from low density APR, we might then reach to increasingly an increasing amount of quark matter effects. First, in terms of quark substructure effects in nuclear matter, they develop delocalized quark matter, which we then should observe so as in the cores of high mass pulsars. So these are two scenarios where we make use of mixed phase constructions. So now I would like to shortly remind you on the theoretical basis of the quark matter model, which we are today discussing. So it is a so-called string flip model. We want to base the equation of state of quark matter on a confining model. So therefore, we went back to the old idea of the string flip model, which was created at MIT by Jack Horowitz, Ernie Moniz, and John Nägele. And parallel to this, we in Rostock and Rossendorf with Hartmut Schulz and Gerhard Röpke developed a statistical description of this string flip quark matter. And nowadays, we have a relativistic formulation using the path interval and an energy density functional U, which depends on quark bilinears, which correspond to scalar or vector densities, which, as we know, should be obtained as derivatives of the thermodynamic potential. And in this way, there will be a self-consistent approach to this density functional. So when we carry this through, so we postulate a general density functional, which we will specify a bit later, and we make a series expansion, a Taylor expansion here, and we stop this Taylor expansion at the first gradient term, where the gradient of the then functional are then scalar and vector self-energies for the quarks. Then we arrive at an effective model for the partition function, which we can solve, because the quasi-particle action, which we have just derived, defines an inverse propagator, which is a quasi-particle propagator. It looks like the free fermion propagator, but it just is an effect potential and an effective quark mass, much like the Blaschke model. And we have a self-consistent potential here, which is given by our density functional and by self-energy times corresponding density. And this functional makes sure that we are always in the minimum of the thermodynamic potential. Now, okay, this can be true. What density functional? Here, this density functional can be more general than, for instance, the Lamborghini-Lazino model. The Lamborghini-Lazino model would be a limiting case where the density function would be just a square of scalar and vector densities. So we keep here this vector density behavior. We even generalize it to a nonlinear behavior because we are interested in the high density stiffening of quark matter, and but obeying the causality constraint. And the dependence on the scalar density is modeled such that the self-energy mimics quark confinement. So it has a dependence on the scalar density with an exponent -1/3. This density to -1/3 would be the mean distance between quarks. And so this is something like a linear confinement potential. The D parameter can be also density dependent. It plays the role of the string tension, and this string tension can be modified in the medium, for instance, by adopting kind of extruded volume mechanism, which is motivated by the dual Meissner effect explanation of confinement. And here's a picture which explains this. In low density matter, all the hadrons are nicely separated, and the non-perturbative vacuum compresses their color flux tubes to linear potential strings. But in dense matter, when the nucleons come close to each other, we use up the non-perturbative QCD vacuum. And so there's a reduction of the external pressure, which compresses the field lines, and they develop the typical dipolar structure of the one-gluon exchange, which we usually have at short distances only. So this is an effective screening of this confining effect. Now, what are the results? So we can construct a usual Maxwell our quark-matter equation of state and pressure versus chemical potential is this violet dotted line. For the hadronic equation of state, we refer to the DD2 class, but here with excluded nucleon volume effects, which have been introduced by Stefan Tüppel in this paper 4 years ago in EJ. And the excluded volume parameter here is a free parameter. And here we see how the high density stiffness depends on this parameter. The pure DD2 equation of state is a black line. The stiffer the matter in pressure versus chemical potential, the flatter this function. So the yellow line is the one which is the stiffest equation of state. This we see when we plot pressure versus energy density. Here we have the typical plateau of the first order phase. Occurs very early, so actually here at about 50 MeV per Fermi cube, below 100, as we have discussed in the introduction. And there's a large jump in energy density before we reach the border of the quark-matter phase. Now we can do a equation. Also, we can use to vary our quark-matter equation of state and fix hadronic equation of state. And then take this set of hybrid equations of state. They all fulfill the causality constraint. Sound is less than the speed of light. And independent of on this alpha parameter, which stands for the screening of the string tension, we obtain late at about 2 solar masses or an early well below 1 solar mass onset of quark-matter. First with an instability, so these gray stretches are unstable sequences, which will only show to guide your eye from where is the endpoint of the hadronic configurations and where does the disconnected third family of hybrid stars start. So this equation of state is able to, in a microscopic approach, describe the mass twin effect and the third family configurations of very compact hybrid stars. Now, let us come to South America in a long-standing collaboration with a group in Argentina with Norberto Scoccola, Daniel Gomez-Dum, and Gabriela Grunfeld. We have developed a non-local chiral quark model, which I will not discuss very much in detail here, but this is the basis of an effective modeling of quark matter, which we will apply, or which we have applied in the last year in a collaboration with Buenos Aires, and including David Alvarez Castillo. And here I show as the full bold lines, the different hadronic equations of state with different stiffnesses, as we have discussed. 3 examples of the DD2 class with increasing stiffness here in pressure versus chemical potential, and the APR equation of state, which is clearly the softest equation of state. Now, when we overlay these hadronic equations of state to a series of these non-local chiral quark model equations of state, which are ordered here according to their stiffness, the stiffest ones are the blue ones. In the middle are the magenta lines, and the softest one are the black lines. So the stiffness you can dial with the coupling constant GV in the vector density interaction. Now we observe the following situation. For APR, we have a crossing with the quark-matter equation of state, but this makes no sense in the sense of a Maxwell construction, because according to Maxwell construction, we should always go along the line of the higher pressure. So this would mean, in the case of APR equation of state, that at low densities, so low chemical potentials, we should go along a quark-matter line, and then we have a crossing, and then we switch to hadronic matter. So hadronic matter at high densities and quark matter at low densities. This obviously is nonsense. So why? Yeah, because at high densities, the ABR equation of state is no longer good. And at low densities, obviously, this equation of state might be, these soft equations of state might not be realistic. Let us like the equation of state or the DD itself. For DD2, we obtain an interesting effect, namely, equation just lies on one of these quark-matter equations of state. So one calls this after Alford and Crater's effect. So we have here a hybrid equation of state, but it is indistinguishable from a nuclear equation of state. If we would stiffen our DD2 equation of state by adopting excluded volume for the nucleons, then of course we can construct a normal Maxwell construction. However, for today's talk, we would like to discuss not only the normal phase transition construction, but also what to do in the case when we have stiff quark-matter equations of state at high densities, which we tend to believe, and a soft hadronic matter equation of state at low densities, then how to join these two regions. For this, interpolation constructions have been invented. So here used interpolation to actually mimic the string equation. So we'll not go very much into the details. So here with this interpolated quark-matter equation of state on the basis of the collaboration with the Argentinian group, we can reproduce the same behavior of Mars radius hybrid stars with the third family in the string flip model. So this last local chiral quark model is capable of reproducing the density functional approach. Now I come in the final part of my lecture to the applications. Two kinds of applications I would like to discuss. The normal case, this is when we practically generalize the ordinary Maxwell construction. Let's say in this scheme, in this sketch, we have a blue hadronic equation of state and a red quark-matter equation of state. The Maxwell construction would define a critical chemical potential. To the left of it, we have hadronic equation of state, and then we switch to the higher slope. So we can generalize this, and this actually would then mixed phase or pasta phases in the phase transition region when we define an on and an end point of this pasta phases or of the mixed phase between hadronic and quark matter. And this phase construction uses a polynomial ansatz, and we see here just a parabolic ansatz, which introduces one extra free parameter, namely the offset of the pressure at the critical Maxwell chemical potential. We call this delta P. All the other parameters can be fixed by the continuity of pressure and density at these matching points. With such an ansatz, we've obtained the mixed phase equation of state. So here on the right-hand side, you see pressure versus energy density, where the plateau type equation of state with constant pressure in the mixed phase is ordinary Maxwell construction. The pasta-like construction has the slope in the transition region. And the corresponding speed of sound then is not zero in the phase transition region, but it is finite in the phase transition region. So here on the left-hand side, we show the hybrid star configurations. They have third family branches, which are describe hybrid stars with rather small radii, but well in accordance with constraints from the tidal deformability. Okay. Now, these tidal deformabilities can be shown here as a function of the mass of the star. We have an interesting situation in this mass range when we have overlapping branches of the tidal deformability, which can, for certain parameters of this equation, they can lie in the region where we have our binary merger, GW170817. And then the lambda1, lambda2 plot can have different branches for the diagonal case. So when we have second family, opposed to the line of equal tidal deformabilities, and we have then other islands. So it would be interesting whether in future systematic studies of tidal deformabilities, such a picture of a multi-peaked structure in the tidal deformability could emerge. Okay, we have performed Bayesian analysis, and here let me flash the result. So this is the corresponding result when we use as a constraint the maximum mass from the Fermati pulsar, the tidal deformability, and the nicer mass radius constraint. Then of our hybrid equation of state, the very low quark matter onset would be favored. So this has actually a phase transition for very low pressures, below 20 MeV per femtometer cube. Okay, so practically all hybrid stars, which we know, all stars, pulsars, which we know would then be hybrid stars, but they would all look like being described effectively by an APR type equation of state. So, and if you believe my argument or the argument of the Japanese group, that APR is good on Earth, and therefore we should not believe it in the skies, then we would have a very strong argument here for an early onset of quark matter in hybrid stars. Now, what would happen if NICER would measure more precisely? So if we just reduce the error ellipse, then magically the onset of matter in compact star moves higher up, so actually a little bit above 1 solar mass, so between 1.2 and 1.4 solar masses. And this would be then the corresponding, in our two-parameter plane, this would be the corresponding Lego plots of the Bayesian analysis. So, now the mixed phase region covers a little bit larger pressures. And we can actually then play with the actual radius ellipse. And this we have done here. So we have shifted a little bit the mass measurement of a fictitious NICER measurement, and we obtain then the corresponding region for the phase transition around.
We have just a couple more minutes and time for just a few questions, David.
Okay, I'm coming to the end. So I would like to show the anomalous case. This is a very interesting case, which was advocated by Toru Kojo, but before by Hatsuda, Masuda, and Takatsuka, and also by Bain and others. And here we have the situation that hadronic equation of state and quark matter equation of state would not cross, but we can say, okay, at low densities, we believe the hadronic model. At high densities, we believe the quark-matter model, and we make an interpolation. So here we suggest actually a very sophisticated two-step interpolation with hadron-like branch up to a critical chemical potential, and the quark-like branch higher densities. So the construction can be fixed, and with this we have described a hybrid equation of state on the basis of the APR equation of state. Here, this is then the fantastic speed of sound square plot of density. The effect of this hybrid construction is a stiffening of the equation of state relative to APR, which is too soft, as we know. And my discussion then, also finally, we can also discuss tidal deformabilities very well in accordance with the modern constraints. And we make the Bayesian analysis and with the basic constraints, but in addition, we can also use the Red-Solar constraint on the upper limit of the maximum mass. This gives a narrowing of the Lego plot, and a further narrowing is obtained if when the nice would be more precise than it is at present. So here comes a kind of conclusion. So this is the mass radius plot once more for these constructed hybrid equations of state. We see an early onset, but what is this special interpolation construction? So is this now quark-matter? So we have two regions. We have a hadron-like region. So here we could say the physical interpretation would be quark substructure, would be Pauli blocking as a stiffening of still hadronic matter, well identifiable nucleons, but with quark substructure effects. And at higher densities, then quarks delocalize. We form delocalized quark matter, which still is very stiff, maybe because of the multi-pomeron exchange mechanism, which survives also the phase transition and leads to very stiff high density matter. Okay, so this is a kind of conclusion. I would like to advertise a recent work by Mahbubeh Sharbaf and myself and a colleague from Iran, which is in Journal Physics of G to appear. We have here applied both constructions to discuss the hyperon puzzle. So we have a hyperonic APR type equation of state. It's called LOCV, so lowest order constraint variational method with an AV18 potential, including hyperons. So this is the red curve. Then the quark-matter curve is the blue one. And here we should, on the left-hand side, we should apply this Kojo type construction. So the anomalous interpretation. In here, hybrid configuration, which actually avoids the so-called reconfinement problem and can describe as massive as 2 solar masses stars, including hyperons. And the opposite situation is in this case when we have a phase transition, but we can discuss Pastor effects, and this would then modify the hybrid equation of state in the region of the onset of hyperonic matter. Still hyperonic matter will then, this due to the quark-matter phase transition, we can reach 2 solar masses. So I will not discuss this as an outlook. I have these applications to supernova and mergers. So we have shown in a work in Nature Astronomy already now almost 2 years ago that a strong phase transition to quark matter can serve as an explosion which actually blows off a very massive progenitor star of 50 solar masses, which for which the ordinary neutrino-driven supernova explosion mechanism would not work. The phase transition mechanism works, and this was one of the great results. Another great result is a study of the gravitational wave signals of the post-merger with a strong phase transition, where we observe a shift of the peak frequency to higher frequencies because of compactification of the matter. And when we plot now two observables, namely the post-merger gravitational wave against the tidal deformability of the pre-merger, then we see that with a hybrid equation of state, we are 5 sigma of the purely purely high scenarios. So this is something will be observable in the near future. So we have generalized this. So there's a great work of many equation of state of this kind with a phase transition, which you find on this archive. Also, the question has been investigated. So what about an early onset of quark-matter in these studies? So this has been recently investigated by Andreas Bauswein with this model-based equation of state, which we have developed, which fulfill 2 solar mass constraints, but have an early onset. And then we see also in this case, this merger peak frequency significantly deviates from.
Please excuse me, David, but we're totally out of time. We won't even have time for questions.
This is my last slide, which shows that. Yeah, so I'm stopping here. So I only want to advertise that we are now in this multi-messenger era where not only neutron stars are constraints for possible phase transition here in the t=0 plane of this 3-dimensional phase diagram, but with supernova and neutron star mergers, we appears also in this finite temperature range where state of matter is maybe similar to future high density and low temperature heavy ion collisions at Nika and Requix-Target and at FAIR, for instance. So, and then we can investigate what is the nature of the phase transition in this region. Is it a first order or the crossover? What is it? So, and
thank you for a great presentation.
Thank you for the attention.
And we don't have time for questions, but if you go to the chat, or not the chat, the Q&A, David, maybe you can answer some of them in writing, even though we don't have time to do them live right now.
Mm-hmm.
But thank you very much. That was very good.
Thank you very much.
Thank you, David.
So our next speaker will be Lucas Nan from the National Autonomous University of Mexico, and he will talk to us about a virtual tour of the recent results of the Pierre Aga Observatory.